I believe I said that we were just going to work some more example problems for today. And so that is 100% what I intend to do. I have prepared literally nothing. I am just going to crack open this random textbook having to do with circuit analysis from my shelf and just look at some problems pertaining to transient analysis of RLC circuits. There's just first order, here's second order, great. Blah, blah, blah. Problems in the back of the chapter. Okay, okay, this one looks interesting. So in this particular circuit from this random textbook I've just pulled out of my office, we have the following circuit. We've got a 40-volt source connected to a 4 kilo ohm resistor. Here is a terminal. Here is another terminal. And here is our switch. So let's call this guy A and this guy over here B. Our switch is going to change states as always at t is equal to 0. There's a 3 kilo ohm resistor. Here's a 6 kilo ohm resistor. Here's a 500 millihenry inductor. Here's a 20-volt source. And lastly, this is an interesting number, so I have suspicious that this might be a critically damped circuit. We'll see in a moment. 781.25 nanofarads. So I'm suspicious that they use such a very specific value for the capacitor to force this guy to be critically damped, but we will see if my suspicions bear out shortly. The signal that they ask us to find in this textbook is this voltage, which they have labeled as V naught of T. And that seems like as good as any other thing that we could possibly be interested in. So that's what I'm ultimately going to try to solve for here. Okay. Just while I'm at it, I'm going to go ahead and label some other things. So this is the voltage drop across my capacitor during the transient condition. This is the current flowing through my capacitor during the transient condition. This is the current flowing through my inductor during the transient. And this is the voltage drop across my inductor during the transient. So let's analyze this circuit and see what the hell's going on. So as per usual, I'm going to start by analyzing at t is equal to 0 minus. So this is a DC steady state condition the moment before the switch has changed states. So effectively, that 3 kilo ohm resistor across the top is going to be disconnected. And so to make this just a little bit less things going on, I'm just going to choose not to draw that 3 kilo ohm resistor at all, since we can hopefully all see very easily that since it's open circuited on one side, it isn't going to do literally anything at 0 minus. So the circuit that we're interested in should look something akin to this. So I've got my 40-volt source down here, positive polarity on bottom. This is my 4 kilo ohm resistor. This open circuited set of terminals here represents my capacitor voltage. So this is, or excuse me, my capacitor. So this is VC at 0 minus, and this is IC at 0 minus. Across here, I have my 6 kilo ohm resistor. This is essentially the voltage V naught of, actually, not even gonna bother drawing that. We'll figure that out at the very end, like we've done everything else. This short circuit right here represents my inductor. And then here is my 20-volt source. So, and let me just label, here's IL at 0 minus, and here's VL at 0 minus. All right. So I think you guys are welcome to disagree with me if you're so inclined. That I can just look at this thing and at least tell what the voltage drop across the inductor is and the current flowing through the capacitor is, and both of those quantities are going to be zero, right? The voltage drop across the inductor at 0 minus should always be 0 volts because we're taking the voltage drop over a short circuit. And the capacitor current at 0 minus should always be 0 amps because we're finding the current that's flowing through an open circuit. The other two quantities are going to be a little bit more difficult, but not super crazy. So anybody have any thoughts on either IL at 0 minus or VC at 0 minus? So I believe you are incorrect about VC and you're partially correct about IL. Okay. So let's look at IL just really quickly. Okay. So these two voltage sources are connected in series and they have the same polarity, so they're going to add together. So we can either treat that as a 60-volt source positive polarity on bottom on the left-hand side of the circuit, or a 60-volt source positive polarity on top on the right-hand side of the circuit. I'm going to choose to look at it as if it were a 60-volt source positive polarity on top. We also have a 4 kilo ohm resistor and a 6 kilo ohm resistor in series, so that looks like 10 kilo ohms. So we should have negative 60 volts over 10 kilo ohms, where I'm saying negative, because if I combine those two sources into a single source on the right-hand side of the circuit, we would expect that to be driving current counterclockwise around this loop, and our IL current is defined as clockwise. Okay. So 60 over 10 is 6, and volts per kilo ohm gives me milliamps. So this is negative 6 milliamps if my mental math is correct. By all means, correct me if it isn't, but I feel pretty strongly that I can divide 60 by 10 without screwing that up too hard. So now that I know what that inductor current IL at 0 minus is, it should be much easier for me to figure out what the voltage drop across my capacitor is, right? So using Kirchhoff's voltage law, we would see that VC at 0 minus is just going to be 6 kilo ohms times IL at 0 minus plus 20 volts. So 6 kilo ohms times negative 6 milliamps is negative 36. 6 times negative 6 plus 20 is negative 16 volts is what I get. Does anybody have any questions, comments, or concerns about how we calculated IL at 0 minus or VC at 0 minus? All right, nobody is saying that they're not catching what I'm throwing, so I can only assume that, yes, Kobe.
IL, you basically just did the voltage drop from 40 to the 20.
So I used a source combination. So the 40 and the 20 are in series. So if I follow that current IL around the loop, IL is flowing into the positive polarity terminal of the 20-volt source, and it's flowing into the positive polarity terminal of the 40-volt source as it circles its way all the way around. So since those two voltage sources are of the same polarity, I can just add them together. So 40 plus 20 is 60. So essentially, I've scratched that guy out and replaced it with a 60-volt source over here. Now, just using Ohm's law, I can see that the current that's flowing out of the positive polarity terminal of that 60-volt source is 60 over 10 kiloohms. And that is in the opposite direction as we have defined IL, which is where this negative sign comes from. Sure. Because it's the voltage drop across the short circuit, which is defined to be 0. So if I have a resistance of 0 ohms, Ohm's law says that V is equal to 0 times whatever current is flowing through there, which is always going to be 0 volts. Any other questions, comments, or concerns? All righty. So let's analyze what's going on at t is equal to 0 plus now. So at t is equal to 0 plus, our switch is now closed at position B. So that practical voltage source on the left-hand side is essentially going to be open circuited or disconnected. So just to make things a little simpler on myself, I'm not going to bother drawing it anymore, okay? So I'm going to have my capacitor here, which is going to look like a negative 16-volt source, positive polarity on top, because VC was defined as positive polarity on top. This is a 6 kilo ohm resistor. This is a 3 kilo ohm resistor. My inductor is going to look like a current source, driving a current of negative 6 milliamps to the right, because IL was defined to be flowing from left to right. And then lastly, I have that 20-volt source like so. So just to be clear here, this voltage is VC at 0 plus. This current is IC at 0 plus. This is VL at 0 plus. And this is IL at 0 plus. So we know that VC at 0 plus must be equal to VC at 0 minus, because the voltage drop across a capacitor cannot change abruptly. So that has to be negative 16 volts, which is why there's a negative 16-volt source there. Similarly, we know that IL at 0 plus must be IL at 0 minus. So that's going to be negative 6 milliamps, which is why there's a negative 6 milliamp source replacing the inductor. And so now we need to figure out those other two pieces. So before I start throwing stuff out, anybody have any thoughts? So I heard two different things. Can we combine those resistors? Absolutely. So 3 and 6 with, excuse me, 3 in parallel with 6 should be 2, I believe, because 3 times 6 over 3 plus 6 is 2. So I could simplify this and just make this a single 2 kilo ohm resistor. So that could be useful. I think I also heard somebody say that IC at 0 plus will just be 6 milliamps, which I agree with, right? So IL is flowing in the opposite direction of IC around this single loop circuit. So if IL is negative 6 milliamps and IC is the same current but in the opposite direction, it must be positive 6 milliamps. So how would we figure out VL at 0 plus? But what about the voltage drop across the resistor? So I would wind up doing KVL around this loop, and since I know the current flowing around the circuit, VL at 0 plus is the only voltage I don't know. So I might do something like negative 16 volts plus 2 kilo ohms times IL, which is negative 6 milliamps plus VL at 0 plus 20 volts is equal to 0. And so solving this guy for VL, let's see here. So add 16, subtract 20. So that's minus 4. And then add 12 is positive 8. Let me just double check. Negative 16 minus 12 plus 8. Well, I should turn my calculator on. Negative 16 plus, excuse me, minus 12 plus 8 plus 20 does indeed equal to 0. Anybody have any questions, comments, or concerns about how we got all those? Ian?
Clockwise, and that is the negative polarity of the negative 16 volts. Wouldn't that be positive 16 there, or is it so negative?
Very good point. I believe that I have made a mistake because I do see the negative polarity terminal first of a negative 16 volt source. So you're 100% correct. That should be positive 16. Thank you for that catch. So that changes things pretty significantly. So we would have, let's see, negative 36 minus, excuse me, plus 12, right? Is 24. I'm trying to figure out if it's a plus or a minus here. Let me just do this. 16 minus 12 minus 24 plus 20 is 0. Yes, so it's negative 24 volts. Thank you very much for that catch, Ian. You're 100% right. Okay, anybody else find any other of my mistakes? I don't believe there are any for what it's worth, but I was wrong a moment ago, so I'm willing to admit I might be wrong now. Okay, so now we're going to analyze the circuit at t is equal to infinity. So at t is equal to infinity, that 40 volt source in series with the 4 kilo ohm resistor is still essentially disconnected from our energy storage element, so I'm not going to bother drawing it. I'm going to take Ka's suggestion and I'm just going to replace that 3 kilo ohm in parallel with a 6 kilo ohm with just a 2 kilo ohm resistor, so it'll make it look a little bit easier. So essentially what I've got is I've got an open circuited set of terminals representing my capacitor. I've got a 2 kilo ohm resistor. I've got a short circuit representing my inductance. And then I've got a 20-volt source over here. Like so. So let me just label a couple of things really quickly. So this is VC at infinity, IC at infinity, VL at infinity, and IL at infinity. And I believe we can see what all of these are just by inspection. So VL at infinity is obviously 0 volts because it's the voltage drop across a short circuit. IL at infinity, I believe, is obviously 0 amps because this circuit does not represent closed path. IC at infinity is going to be equal to 0 amps because no current flows through the open circuit representing the capacitor. And lastly, VC at infinity, that looks a lot like an L, so sorry about that, is going to be 20 volts if we apply Kirchhoff's voltage law around this loop. So essentially, since there's no voltage drop across the 2 kilo ohm resistor and the positive polarity terminal of VC is at the positive polarity terminal of the voltage source, they're the same thing. Okay. So now we need to figure out if this circuit is critically damped, overdamped, or underdamped. And also we need to figure out if this is a series RLC circuit or a parallel RLC circuit, okay? So for what it's worth, when we're trying to figure out if it's a series RLC circuit or a parallel RLC circuit, essentially we need to look at this circuit during the transient condition as a dead network, okay? So I'm just going to make a quick sketch over here, right? So I've got my capacitor. I've got, so that's 78.1, or excuse me, 781.25 nanofarads. I have a 2 kilo ohm resistor because during the transient, those two resistors are in parallel. I have my 500 millihenry inductance. My 20-volt source is turned off. And so that looks like all three of those are connected in series to me. So this is a series RLC network, okay? So if there's ever any question about whether it's series or parallel, look at it during the transient and turn all of your independent sources off and then see how things are connected. And that will literally tell you whether it's a series RLC or a parallel RLC.
So we have a combination of both.
So on Monday, we are going to start looking at general second order circuits where they do not easily fall into series connection or parallel connection. But the easiest way to understand how to solve those problems is to have a good grasp of how to solve a series and a parallel first, which is why I started with series and parallel. All right, so series RLC circuit. I believe I have proven that to you all. For a series RLC circuit, alpha is equal to R over twice L, where R in this case is just going to be that equivalent resistance of 2 kilo ohms. And then I have 2 times half of a Henry, so that's just going to look like 1 Henry in the denominator, right? Or 2 times 0.5 H. And so that should be 1,000 per second, 2,000 over 2, right? Or no, so 2,000 over 1. 2,000 per second. Omega naught is the square root of 1 over LC. So that is going to be 0.5 Henrys. Jesus, 781.25 times 10 to the minus 9 farads to the negative 1/2 power. Oh. And I get 1600. Well, I am pleasantly surprised because we have yet to work a overdamped system, and I'll be damned if this one isn't overdamped. Okay. All right. So we've got an overdamped system. So while we're at it, we should probably go ahead and calculate S1 and S2. I'm going to wind up storing these in my calculator here in a moment. So S1 is always negative alpha plus the square root of alpha squared minus omega naught squared. So that would be negative 2000 plus the square root of 2000 squared minus, 1600 squared. And I got that to be negative 800 per second. And I'm going to store that in my calculator as A. Just make it easier when I set up my system. And then I'm going to have negative alpha minus the square root of alpha squared minus omega naught squared. So let me just flip the sign on that bad boy at the front. Or I guess in the middle, that comes out to be negative 3200 per second. And I'm storing that in my calculator as B. Okay. All right. I'm going to scroll way back up to the beginning, and I want us to figure out how we're going to solve for that quantity V naught of T. Okay. So before I tell you how I would do it, do any of you have any thoughts? So I'm not entirely sure what you mean by applying KVL at a node, because KVL is usually applied around a path. KCL is the one that's applied at a node. Kaylee, you have any thoughts? Carl, what about you? So it's not just the same as VL, but you're very close. You're missing one small thing, and that small thing is that 20-volt source. So if we were to apply Kirchhoff's voltage law around this path, we would see that V naught is just the sum of the voltage drop across the inductor plus that 20-volt source. So V naught of T is just VL of T plus 20 volts. So it seems like if we can solve for VL of T and then add 20 to it, we're good to go. So that's 100% what I'm going to do. Okay. So since I need to solve for VL of T, my system of equations is going to be my inductor current is my first equation and my inductor voltage is my second equation. So for an overdamped system, we'll say that IL of T is going to be A1E to the S1T plus A2E to the S2T plus IL at infinity. That's it, sorry. IL at infinity was just 0, right? Yeah. So essentially, at T is equal to 0 plus, this reduces down to A1 plus A2. IL at 0 plus was negative 6 milliamps. So we have A1 plus A2 is equal to negative 6 milliamps is our first equation in our system. Let me just double check here and make sure that IL at 0 plus was indeed negative 6 milliamps. I was correct. Josh.
So you just pulled the response equation from the sheet, correct?
Yeah.
So do we have to do that for each Like for what we're trying to find, like, so like for V of L, for V sub C, for V sub C, and then we apply sub C.
Yeah. So essentially, and I mentioned this on the first day that I showed you guys the table, but that function y of t that I gave you is always going to be either the capacitor voltage or it's going to be the inductor current. Okay, those are the only two options. And then the one below it that is the derivative relationship is going to be the other thing, right? Because we know that the voltage drop across an inductor is related to the derivative of the current flowing through the inductor. And we know that the current flowing through a capacitor is related to the derivative of the voltage drop across the capacitor. So we're always going to set up a system of equations where y of t will always be either the voltage drop across the capacitor or the current flowing through the inductor. And then our derivative-based equation is the other thing.
And that won't affect it, depending on if the response type changes, like from under to.
Right, so it doesn't matter what type of response, that's always our approach. Okay, so now we have our second equation. So this is going to be VL of t is L DIL by dt. And that's literally just going to be L times S1 A1 e to the S1t plus S2 A2 e to the S2t. I can do the derivative of this one in my head, thank God, so I don't have to borrow your table again, Andrew. Evaluated at t is equal to 0 plus, this looks like L times S1 A1 plus S2 A2. So let's see, so VL at 0 plus was negative 24 volts. So what I'm going to do is I'm just going to, because I already have S1 and S2, I'm going to say that, let's see, S1, so I'm going to have negative 800 A1 minus 3200 A2 is equal to negative 24 volts over half of a Henry, or just negative 12. You're right, I'm bad at math today, thank you for that. Negative 48. And the units for this guy, I believe, will come out to be amps, because a Henry is a volt second per ampere, so I'm going to wind up with something in amps per seconds, which is it's going to be amps. So I now have two equations, and so I can just throw these into my calculator, right? So if I set up my 2x2 system solver, goodness. Did I screw something up again?
We were just kind of thinking on the A1 and 2. What exactly?
What exactly A1 and A2 are?
Yeah. Is it just what we solve for?
They're those coefficients that we are ultimately trying to solve for, yeah. Yes.
Make sure I understand this correctly, since we're analyzing at 0 plus, we can knock out the E, since that T is technically 0.
Yes, 100%. That's what we've done every other time. That's what we're continuing to do. Yeah. Mhm.
Correct.
Yep. Yeah, so the exponentials are always going to look like 1 at t is equal to 0 plus. All right, so I'm going to solve this system while you guys continue to talk amongst yourselves. Please let me know if there's anything I can help to explain.
Yeah, they're responsible.
So I wound up getting, when I solved this system, so this was equation 1 and this was equation 2, I got A1 to be -7/250 amps, which is the same thing as 28 milliamps. And I got A2 to be positive 11/500 amps, which is the same thing, sorry, that should be a negative sign right there, as positive 22 milliamps. So, I can see, I hope pretty easily that if I'm trying to figure out what the coefficients for my inductor voltage is gonna be, that's literally just gonna be this L times this A1, excuse me, S1 times this A1, right? So L was a half. S1 I have stored in my calculator as A. And A1 gets stored in my calculator because I'm using TI automatically as a variable X. And so I wind up getting, sorry. So let me just write this out explicitly. VL of T is going to be L S1 A1 e to the S1 T plus L S2 A2 e to the S2 T. I got 11.2 e to the negative 800 T. Now let me do 0.5 times what I have stored in my calculator as B times what I have stored in my calculator as Y. Negative 35.2 e to the negative 3200 T volts. And from here, I can say that the voltage that I was interested in is then just going to be 20 plus 11.2 e to the minus 800 T minus 35.2 e to the minus 3200 T volts. So, do we want to throw this into LT Spice and make sure we're correct, or are we good to go?